Talk about section 6.2 in your book about volumes. So we'll start off simple. If you're working with a simple 3D shape, like for instance a cylinder, let me draw it right here. There's a cylinder right there. It's of radius r, height h. You might have learned that, for these simple shapes, it's pretty easy to compute the volume. In this case, the volume is just pi r squared times h, where this pi r squared here is the area of one of these cross sections of the cylinder, because cross section is just a circle. And then h is the height. H is the height of the cylinder. So, when you have a simple shape, it's pretty easy to compute volumes with some kind of formula. But now, what happens if you don't have a very simple shape that you want to compute its volume? For instance, here's some crazy looking 3D shape. It's all wiggly and whatnot. Two end caps here, and then it all wiggles all throughout here. And now you get asked to compute the volume of this thing. Since in general there's not really a closed formula that you can write for this kind of stuff, the procedure, however, is still the same as for simple shapes. What you do is, let's put some coordinate axes down. Here's x-axis, y-axis, z-axis. And if I want to compute, and say the x-axis here goes from like A to B, and then say I'm at some point x right here. Well, if I want to compute the volume of this thing, what you do is you take this volume, you go to a point x that's in the middle of this thing, or just x is arbitrary, just somewhere in between A and B. And then you look at the cross section here at the point x, so this little slice going across. And what you do is you have to compute the area of the cross section at x. How this is done in general, there's not a closed formula for it. We'll look at tons of examples where you can do this, but the idea is you get the area of this cross section, and then at x, and then what you do is you imagine that this cross section here has a tiny bit of thickness to it. Just a tiny bit of thickness to it. This red part here going around. That's where this cross section's just got a little bit of thickness to it. And say that thickness it has, let's call it dx, or delta x, whatever you want to call it. Let's call it dx. And so that gives you a tiny little bit of the volume of this entire thing. Or you just get the volume of this really tiny piece at x with a really tiny width, dx. And so this ax dx is the volume of one small part of the cross section. And now if you want the entire volume, you just add up all the small volumes at all the different cross sections, which means for us you integrate from x equals a to x equals b, all of the cross-sectional areas. This thing is how you compute the volume of a more general solid. That's really all it is. So as an example, let's recompute this, this 3D let's recompute the volume of this cylinder above here, this cylinder above right here, but using the more general method right here. How do we do that? In this case, for the cylinder, radius r, height h. Put the cylinder back down here. You can put coordinates wherever you want. I say I put my coordinate system here so that this is my y-axis, that's my x-axis, and then here's my z-axis. And so that the center, the bottom of the cylinder is at 0, and the top of the cylinder is at height h. And then the radius of this thing is r. And so when you look at one of these cross sections, in blue here, at the height y, the area of the cross section at y is just pi times the radius squared, because you just have a circle of radius r at the cross section, and that's the area of a circle of radius r. So now to compute the volume of this thing, we just use our formula. So we integrate from y equals 0 to y equals h, all the cross-sectional areas with their really tiny thickness dy. In that case, well, a of y is just pi r squared, that's a constant. So we just pull it out. And now when we do the integral just gives us h. And so it's the same as the formula that we were told about, probably taught about earlier in our education, but now we can actually show it. So yeah, so that's at least confirms that the general way of what we're doing is at least consistent with what we already know. So now let's look at some more examples. Let's look at the following example. So now we have a sphere, or I should say a ball, 3D ball of radius r. We want to show that the volume of this ball is 4/3 pi r cubed. So yeah, it's a formula we were taught about in school. Now we're going to actually show it. So how do we do that? Well, we just use what we know. So we put down a coordinate system. Here I'll put the coordinate system at the center. So why not? Okay, there's the x-axis, there's the y-axis, there's the z-axis. And we have to pick one direction to integrate in. I'm going to integrate in the x direction, so why not? Now when I'm at some point x here, I look at the cross-section of this ball at x. The cross-section itself is a circle, and its radius, well, I have to figure out what its radius is, the radius of the circle. So we know that this point here and this point down here, these are 2 points that lie on the sphere, so I know the distance from the center of the sphere to the point here, that's r. And then I know that this distance from the center of the sphere to x, I just call it x, because that's what it is. And then the distance from this point here down to the center of the cross-section, that is my y. And so this point here in black that lies on the sphere, x comma y, I know that for the sphere we have that, we have that, I guess I should be more precise, this is in 3D space, so it's x, y, and then there's no z component. It's the part that's completely in the plane. Anyway, this makes a right triangle here with legs x and y and the hypotenuse r. So so for the sphere, those 2 points, they satisfy x squared plus y squared equals r squared. Okay, so now I can solve for the radius of the cross-section A. The radius of the cross-section is just y equals r squared minus x squared square root. You just solve the equation above for y. And so that the area of the cross-section at x is just pi times that radius squared. So that radius is y, but y is in terms of x, so it's just pi times r squared minus x squared. Okay, that just comes from here. Okay. So now, if I want the volume, we just use the formula we have from above. We have to integrate all of the cross-sectional areas multiplied by their really tiny thickness, dx. And now the question is, what do we integrate from? Well, we did all of our cross-sections in the x direction, so when I look at where x is being integrated from what to what, it's being integrated from out here is the point minus r, or if I'm being very precise, because I'm in 3D, minus r, 0, 0, all the way out to the point here, x equals r. So if I want to integrate everything in x, it's from minus r to r. Now I just plug it in. Integral of minus r to r, pi, the radius of the cross-section, r squared minus x squared, radius of the cross-section squared, if I'm being precise, dx. And now we just are computing this integral with respect to x. The pi r squared part's constant, and the x squared part's just a polynomial term, so it's pretty easy to compute. So I can do that. This gives me pi r squared, x evaluated, x goes from minus r to r, minus 1/3 pi x cubed. X also goes here from minus r to r. And now it's just bookkeeping and keeping track of the computation, but let's finish it off. Pi r squared, x minus negative x, minus 1/3 pi, here, oops, sorry, that was a mistake, r minus negative r. At 1/3 pi, r cubed minus negative r cubed. Okay, now just simplifying that up, this first term becomes 2 pi r cubed. Sorry, not 2 pi r cubed. Yeah, actually, yes, 2 pi r cubed. Yes. And this other term becomes minus 2 pi over 3 r cubed. Okay. And when you simplify all that down together, the final answer you get is 4 pi over 3 r cubed, which is what we wanted to show. So yeah, that's how you use the volume formula to compute. This is how you use the cross-sectional areas to compute the volume. And the key that made this all work was these cross-sections had a simple shape where we could just easily compute the area of them. In this case, the cross-sections we've seen so far have all been circles. The cylinder example, they were circles of all the same radius. Here, they're circles of varying size, but it's okay. We can still handle it. Just draw a picture, use a little bit of geometry, trigonometry, and figure it out. It's not bad. Let's see what next. Now, let's just keep doing some more examples. So here's another example where now, here's the picture in the XY plane, and I have this curve y equals square root of x. This is y equals square root of x as x goes from 0 to 1. And I look at this region under the curve here, so this blue part. So that's an area, 2D region. What I do is I take that 2D region and I rotate it about the x-axis. So when you do that, that creates a certain volume looking shape. I'm not going to try and draw it because I'm not very good at drawing. So the point is, you want to find the volume obtained by rotating the blue region about the x-axis. Okay. Okay, I guess I will try and sketch this a tiny bit. When you rotate this thing, this will create a mirror image down here. And then the cross sections you get from rotating this thing, so now let's add a z-axis. Cross section you get from rotating this thing, if I'm at a point x in here, this creates another circular cross section. It comes out, hits, comes back around, there. So that thing all in green is a circular cross section, and it has a certain radius. The radius is from the center of the cross section to this height here. That height, this height, it's just you have this point x comma y that lies on this curve y equals square root of x. So the height here, I'll call it h. If I want to look at the area of the cross section, do that in green. Area of the cross section at x, it's just pi times the radius. I'll put this in red. Radius of the cross section at x squared. But the radius of the cross section is just that height h, which is the distance from that point y to the to the x-axis. So the point is it's just square root of x quantity squared. Because you just plug in y equals the height that I'm working with is the y coordinate, which is square root of x, because it lies on that curve. So in other words, the area of this cross section is just pi times x. Okay? And now if I want the volume, we just integrate. Now here we're integrating in x, so x goes from 0 to 1, so that's the two bounds of integration on the left and the right here. And we just need the cross-sectional area, which is pi times x dx, the tiny little width of that cross-section turn into a tiny little volume. We add up all the volumes. That's what this integrating is doing. So when we do that, now we can just compute the integral. It's just pi over 2. Yeah. So that's how we obtain this volume from this something that's called a surface of revolution. It's where you take a surface, an area, region, and you rotate it about something. That's how you get that. So that's easy way how we compute that. Okay. Yeah. That next example I want to do. So now I have this region y equals x cubed and y equals 8. So let's put y equals 8 here. And now let's draw this cubic function. Here, this is y equals x cubed. Okay. And the cross, I have this region in blue here that's bounded by all these. Okay. And I take that region and I now rotate it about the y-axis. Okay. All right, so I want to compute the volume from the resulting, take the surface of revolution. Okay. So same as always, when you do this rotation, it creates, let me try and sketch part of it. So if I rotate this thing about the x-axis, and I look at a particular cross-section, the cross-section here at a height y looks like this circle there. That circle has a certain radius at y. This radius is that length there. Okay, that's the radius of that. And so now the area of the cross-section at y is just pi times the radius of that cross-section squared. But what is that? What is that radius? Well, the radius is just the distance from the y-axis to this point here, x comma y, where xy lies on the curve y equals x cubed. So if y equals x cubed, that means then that that x is the cube root of y. And so here this is pi. The radius here is just equal to x, so pi x squared. But x is the cube root of y here, so this is pi times cube root of y squared, otherwise known as y to the 2/3. So that is the area of that cross-section, that circle in red right there. And so now if I want the volume, I integrate in terms of y from y equals 0 to y equals 8. The cross-sectional area at y times its really tiny thickness. So I'm integrating all the really tiny cross-sectional volumes. Okay. So there you go. That's how we set up set up that integral. I'll leave this as an exercise for you. Finish this computation. Because the main idea here is to just make sure we understand how to do the setup. Yeah, I'll leave it to you to work out the rest of it. Okay? Yeah, so that was example 3. Let's call that example 3. Okay. See, moving on. Let's take a look at this other example. Example 4. So now we have a slightly more complicated region, but the idea is still essentially the same. Okay. So we have two curves now. Y equals x. Then we also have y equals x squared. Those, I just know they intersect at 1. So I draw the curve, it looks like. See if I can draw this properly. There we go, looks like that. Now this one is supposed to be symmetric, but there we go. This is y equals x squared. And now the region I'm working with is the region in between the two, right here. So that's the region, and I take that region and I rotate it about the x-axis. Okay? Yeah, so when you do that, it's a little hard to visualize. When you do that, you rotate about the x-axis. You get, say, if I'm at a point X here, the kind of cross-section you get comes out from here is no longer just a disk. Oops, I drew that wrong. No longer just a disk. But you actually get this disk with a hole in it, otherwise known as a washer. Okay, otherwise known as a washer. So my cross-section, if I was looking at it head on, say if I was looking at it, there's a little eyeball, and I was looking at the cross-section in the direction from the x-axis facing that way, my cross-section would look like this. Look like this circle with a hole in it. And the circle with the hole in it, it has an inner radius and an outer radius. So let's talk about the outer radius first. You have this outer radius, so I'll call this RO for R outer. You have this inner radius RI for R inner. Yeah, and so the outer radius here, so let me see if I can actually draw it in colors. So I got this blue line here. That represents this outer radius going all the way to the top part here. So where it lands on the outer radius here, this point, this point that it lands on, let's call this Y1, let's call this Y2. This point that it lands on is the point X, comma, Y1, where this point lies on the curve Y1 equals X, okay? So that radius, the outer radius here, is just that height, Y1. But Y1 equals X, okay? And now we have the inner radius, Ri. Well, that inner radius in black here, if I draw it on the picture here, that's just the distance from x up to the bottom part, up to the bottom curve, y2. So that's just y2. But y2 is x squared. Okay? And so now, if I want the area of the cross-section at x, well, the area of the cross-section is all this part in green here. Okay? But you can think of it as take the area of the circle with the outer radius, so this is pi outer radius squared, and then subtract off the area of the circle with the inner radius. Because that's what you're removing. You're removing that circle right there. Or if I factor out the pi, you get an r outer squared minus r inner squared. And now, since I want this in terms of x, since I did my cross sections in terms of x, it's pi times x minus x squared. Okay, so that's the area of one of those cross sections, one of those washer cross sections. Okay. And now, how do I compute the volume then? Well, it's the same as what we've been doing. Just the particular way we needed to compute the cross-sectional area was a little different, but nothing new here. So it's just the integral. We're integrating in terms of x. X goes from 0 to 1 here in our case. And we have pi times we have the cross-sectional area of the washer. It's a washer cross-section, so it's pi x minus x squared. Just did dx. And now, when you just do the integral, that is pi times 1/2 minus 1/3, otherwise known as pi over 6. I'll let you fill in the details on that later. Okay. So yeah, that's how we compute the volume, where now the cross section, instead of just being a disk, it's a circle. It's a circle with a hole in it. And once again, it's still a simple shape because we know how to compute the area of a circle with a hole in it. As long as you know the two different radii, you just take the outer radius squared minus the inner radius squared and multiply by pi, of course. And that's the formula for that. So I guess I can emphasize this is the outer area of the larger disk minus the inner area of the smaller disk. Okay. Yeah. So that's all of that. That's how you do that example. Now let's just keep cranking on. Let's look at this another example. Let me switch back to black. So now in this example, we're going to rotate about a line that's not one of the axes. So we'll take the same region as the previous example. So let me just set it up, maybe draw the pictures a little bit bigger. So we have the line y equals x, y equals x, and then we have the line, well, the curve. Let me make this curve swoop out a little bit more, really exaggerate it. That's the line y equals x squared. It's not exactly what it looks like if you replot it, but it's just easier to visualize that way. And we have the same blue region here. And now we're going to rotate it about the line. Let's rotate it about the line. Let me move all of this down. Instead of rotating about the line y equals 0, otherwise known as the x-axis, we'll rotate about the line y equals 2. Okay, so let me extend this up a little bit. call that line y equals 2. And I'll put some dashes across this. That's the line y equals 2, and we're rotating that blue region around this axis now. Okay. So now if you were to imagine what that looked like when you rotate all this stuff in blue around, when it hits the XY plane again up at the top somewhere, the picture would look something like this. Okay, so that's the area after it got rotated here. And now the cross sections, so I'm at some point X here. My cross sections that I obtain are just these much bigger washers. So this comes all the way out of the page, all the way around, comes back in. This comes all the way out of the page, all the way around, comes back in here. Then comes back behind here, all the way around. Comes back behind here, all the way around. Okay, and so now we have a washer. This washer in green is supposed to be situated at, centered at the line y equals 2. And now if I look at the cross section, head on, it's still just a washer. It's still it has an outer radius and it has an inner radius. It's just how we compute the outer radius and the inner radius is a little bit different now. So here now, because everything is with respect to this center line y equals 2, if I look at what the outer radius is, that is the distance from here all the way down to the curve that's farthest away, the point on the curve that's farthest away. So that's all the way down here. So this is my outer radius. And now my inner radius is the distance to the curve that's closer. To the point on the curve that's closer, that's our inner radius. Okay? And so now if I were to just extract out some parts of this picture to make it a little less cluttered, we have the line y equals 0 here, y equals 2 here, so this is at the point X, and now up here at the bottom curve we have, let's call it, let's be consistent with what I had before. In the first one I had y2 was x squared and y1 was x, so let's call it the same here. y2 is x squared, and then y1 equals x. Okay, so here we have y2 equals x squared, and then up here we have y1 equals x. Okay, so y2 is x squared. That means this height here is x squared. And it says y1 is x. It means this height here is x. And then let me put a different color out now. This part here in red that I'm missing is the inner radius. And this part in blue that I need to figure out is the outer radius. And so to figure all this kind of stuff out, you just look at the different you just look at the different pieces and see which ones add up to what you know. So what I mean by that specifically is, if I want to figure out that's supposed to be outer radius. If I want the outer radius, if I just read off what this is saying, so that is the distance x squared, and then the blue to the blue is the distance outer radius, which I'm trying to solve for, and both of those pieces should add up to 2, because that's the whole height of this thing. So you have our outer radius plus x squared equals 2. In other words, the outer radius is 2 minus x squared. Okay. Similarly, if I do the same stuff with the inner radius, so I have this entire height here is x, and that entire height here is the inner radius I'm trying to solve for, and that also adds up to 2. So you just read off what the picture is telling you. Inner radius plus x equals 2. That means the inner radius is 2 minus x. Okay. So now that I have the outer radius and the inner radius, I can compute the area of the cross-section at x. That's just pi outer radius squared minus inner radius squared, or from what I just did, pi 2 minus x squared, quantity squared, minus 2 minus x squared. Yeah. Yep, that's what that is. So now that I have the cross-sectional area at the point x, the volume, just to finish it all off, now we still integrate. Let's go back up to the picture. X here goes from 0 to 1, because that way when we sweep that out, that gives us the entire volume, because we're just adding up all the cross-sectional volumes. Yeah, so x goes from 0 to 1. The cross-sectional area, which is 2 minus x squared, quantity squared, minus 2 minus x, all that squared, dx. And now I'll leave this part as an exercise to you to finish that computation. It's you just multiply out the polynomial and just do it. It's not bad, but I don't want to do it. Okay. I think I'll go ahead and do this other example as well. Just to show what's happening. So we're going to work with the same region again, but instead of rotating it about an x-axis or a line parallel to the x-axis, we're going to rotate it about a line parallel to the y-axis. So I think I need to make this a little bit bigger. Well, once again, same scenario, 1, 1. Here's the line y equals x from there to there. Here's the line, extend it out a little bit, y equals x squared. I have the blue region. Now we're going to rotate it about the line x equals negative 1. And now with what we're doing, since this is the only method that we know that our cross sections that we get are going to be formed by taking, if you're at a height y now, when you're doing things with this method, also known as the washer method, your cross sections are always going to be perpendicular to the axis that you're rotating. Perpendicular. So when you do this perpendicular cross section and you rotate it around, say all that stuff there, rotate it around, and we look at the cross-sectional area, we want to look at how do we compute the cross-sectional area of this? So the cross-section is just a washer, so we need the outer radius and we need the inner radius. Here now, the outer radius, the outer radius is always the distance from the axis you're rotating all the way out to the, from the axis you're rotating all the way out to the farthest part of the outermost part of the washer. So this is my outer radius, while my inner radius is always the distance from the axis you're rotating about to the inside part. Okay, the part that's closer. Okay. The picture I drew here is misleading. Let me fix that. Here's the point 1 out here, and now here's the point, the x coordinate for the outer radius, and here's the x coordinate for the inner radius. Okay, so now let me just declutter this picture a little bit. Okay, so here's the origin, that's x equals 0, here's -1, here's 1, here's the point x0, here's the point xi, okay? Now this distance from -1 up to that coordinate xi that we don't know what it is yet. This is my inner radius. The distance from -1 up to that coordinate x0, that is my outer radius. Okay. Okay. So first, let's talk about what xi and xo are. Well, xo, the point xo comma y lies on the curve y equals x squared. So this means that y is x0 squared, which means x0 is square root of y. Okay, positive square root because everything over here is positive. Now, similarly, the point in blue, xi, y, lies on the curve y equals x. So y equals xi. Okay? Good. So that tells me what the 2 points xi and xo are. In terms of y. Why do I need them in terms of y? It's because at the end of this, when I find the cross-section at y, I have to integrate with respect to y. Yeah, that's how all this works. Okay. What next? So now I need this inner radius. Well, the inner radius, I can just read off. The distance from -1 to 0 is 1. The distance from 0 to xi is xi. So that means that this all implies, just from reading the picture, the inner radius is xi plus 1. Okay? And now, similarly, the outer radius, so that's distance is 1, and now the distance from all of that is xo. This says that the outer radius is xo plus 1. That's the inner radius and the outer radius just from drawing a picture. Now we can compute the cross-sectional area at y, just pi inner radius squared minus outer radius squared. Let me go ahead and fill these in terms of y. And this is square root of y plus 1 from what we did above. So now you got the outer radius squared, square root of y plus 1, all that squared, minus the inner radius squared, which is y plus 1 squared. Yep, that's what that is. And now the volume you get from rotating this about the line x equals -1. You integrate now, y goes from, y actually still goes from 0 to 1. Yeah, it's not always going to be like that, but in this case it is. Area, volume, we integrate y from 0 to 1. The area, cross-sectional area at y, pi square root of y plus 1 squared minus y plus 1 squared dy. And then you just finish computing all that stuff out. I'll leave that to you as an exercise. At least that's how you set it up. Okay. So what were the what's the key takeaway here is that when it comes to computing this cross-sectional area, there's not always going to be a very clean-cut formula for how to do it. You really, to do well at this, I really think you need to draw a picture and just sit down and think. Like, that's really the only way to get this, to consistently get this cross-sectional area without making a mistake. But there are some key themes, like as long as you just keep track of what you're doing geometrically. Like if I have my axis of rotation, the outer radius is distance to farthest part of the curve, the farthest part here. So the curve that's farthest away from the axis. Center radius is always distance to shortest part of the curve, okay? And then when you look at using this washer method, the cross section here, it's always a washer, so you take the area of the larger disk, the larger circle, pi r outer squared, you subtract off the area of the smaller circle, pi r inner squared. And how you actually compute this inner radius, outer radius, it's best done with just a picture. That way you don't accidentally get a sign wrong where you accidentally subtract one here instead of add one or do something, whatever. It's just, in my head, it just makes a lot more logical sense to just get good at drawing pictures. Get good at drawing pictures and doing this kind of process here, like I showed, where you take the points you're trying to solve for, you plop them down on a number line, and you just read what the distances say. You're computing this distance two different ways. One way is the inner radius that you don't know. The other way is it's just this distance 1 plus xi, and xi is something you do know. So that's how you get this equation. This is that. Same thing with the outer radius. You just computed the distance two different ways, so you get this is that. Yeah, that's really just going to be the best way to do it. Okay. It doesn't matter if you're integrating. It doesn't matter if you're rotating about the x-axis, if you're rotating about the y-axis. When you use this method of integration, this method of computing a volume known as the washer method, it's the similar setup. No matter what, it doesn't matter if you rotate about some axis or that's not. If you rotate about a line parallel to the axis, or if you rotate about the axis itself, there's a lot of stuff that's common here, and you do it a few times, get some practice under your belt, it'll make sense. Okay. Let's see if there's anything else I wanted to talk about. Yeah, so this volume stuff, we did a lot of exercises with volumes of revolution, but that's not the only type of volumes that are out there. Yeah, let's just go straight into the example. So yeah, this example 7. Now, the scenario is this. So I'm actually going to draw my axes a little bit different than what I've shown before. Here, I'll make this the x-axis, and I'll make that the y-axis, and now that's the z-axis pointing up. Okay? So the normal xy plane, I've just turned it on its side. And now say I've got a circle of radius 1. Okay? Circle, radius 1. And now, let's say on top of the circle, I put some cross sections that are parallel to the y-axis, perpendicular to the x-axis. I have one of those cross sections there, okay? And at this cross section, let's say I have a equilateral triangle, okay? So this is an equilateral triangle. It has side lengths S, S, S. And what S is depends on where I'm at in the coordinate X here. So that's that side length S, okay? And let's say I do that for all of the cross sections here. So I go to the next cross section here, and I have a larger equilateral triangle, okay? And at this next cross section here, I have an even larger equilateral triangle. And you see that if you were to patch all these together, it would make a very strange looking cupped like pyramid thing. It's kind of hard to draw, but the point is that each one of these cross sections, so at each value of x, I decide to plop down an equilateral triangle that's pointed up in that direction. So that creates a 3D volume. Okay? And now the point is we want to find the volume. Well, computing the volume is still the same as always. It's just the volume, as we integrate, x goes from -1 to 1. The area of a cross-section at x, dx. It's the same as it's the same formula. But what's a little different now is how we compute this area of a cross-section. Well, here, this is the area of the equilateral triangle at x. So at x, I have this equilateral triangle. This equilateral triangle, say one of these, its two sides, it's one of its sides touches these 2 points here, x minus y and x comma y. It's y minus y because of symmetry. And I just know that xy lies on the circle. So I know that x squared plus y squared equals 1. Which means then that I can solve for y in terms of x. Y equals 1 minus x squared. Okay? And so taking this equilateral triangle and taking the picture all the way here, here's the point x comma y, here's the point x comma negative y. And so this side length s at x is just twice, it's just 2y. Just 2y. Because it's this y minus the negative y. That's the distance there. But y is in terms of x, because they both lie on these points lie on the circle. So it's 2 square root 1 minus x squared. Okay? And now this is an equilateral triangle, so all three of its sides are that length. And now if I want the area of this triangle, at x, it's just 1/2 base times height, but we weren't given what this height is. So you can either look up a formula for the area of an equilateral triangle and remember it, or if you're like me and you don't remember, you do know that equilateral triangles have angles of 60 degrees. And so if you look at this right triangle here, it's a 30, 60, 90 triangle. So you could use just trig from that. Or if you completely forget your trig stuff like I do, you can also just use Pythagorean theorem, where this length here is the side length over 2, and the hypotenuse is the side length of x, so you can solve for it. H squared plus the side length x over 2 quantity squared equals the side length squared. Which means h squared is 3s squared over 4, which means h is square root of 3 over 2s. Okay, so that's the height. So now the area is 1/2 the base, which is s of x, times the height, which is 1/2 times s of x times square root 3 over 2 s of x, which is square root of 3 over 4 s of x squared. So to just jump from here, in case you forgot, the area of an equilateral triangle with side length x, it's just equal to square root of 3 over 4. Oh, sorry, not side length x, with side length s x, it's just root 3 over 4, the side length squared. Okay. So yeah, no, if you remember that, just jump straight to here. But if you're like me and you don't remember it, you just draw the picture and then you do the steps and you just remember it that way. Okay, so that's the area of that equilateral triangle. So now when I come back to this volume computation, it's integral minus 1 to 1, square root of 3 over 4. Now s of x in terms of x is this, so I just substitute that in there. S of x squared would be 4 times 1 minus x squared. All this is square root of 3, integral minus 1 to 1 of 1 minus x squared. Oop, forgot the dx. And now you can finish it off exercise. So the point is, the theme is, no matter what, computing a volume, you find a cross-sectional area, and then you integrate. That's all you do. It doesn't matter if the cross-section comes from an area of revolution, or if the cross-section comes from doing a silly little construction like this. It's just, it's the same thing every time. It's the same thing every single time. Okay. That's section 6.2, how you find volumes in general. It's just you integrate the cross-sectional areas, and then we saw a couple special cases where you could do some tricks. Yeah, that's all.